Hi, it's time for AP Chemistry Review. It's me, Dr. V, and I'm here to help you get ready for the AP Chemistry exam in May. We're working today on free response question number 5 from the 2019 released exam. It's a short free response question, and it's scored out of 4 points. I always recommend that students try to write out their own solution to all the parts of the question before they listen to my explanation. To do this, you'll need your calculator and your periodic table and your formula sheet. Try to do all the parts. You can do all the parts on your own, all together, or do a part, listen to the explanation, do a part, listen to the explanation, whatever works for you. But this is really beneficial to students in terms of getting a feel for how much detail they need to put in their answers and making sure that their answers really reflect and demonstrate their knowledge of chemistry. And then keep track of your score for each part as you listen to my explanation. That's also a really helpful thing for students. So let's jump right in to the problem. The complete photoelectron spectrum of an element in its ground state is shown here. All right, so it's a complete spectrum, which means all of the electrons in the atom are represented. And it's in the ground state, so all the electrons are in their lowest energy levels. Okay. For these PES spectra, the x-axis is the binding energy per electron. How much energy do I have to put in to kick electrons out of the different sublevels? And then the y-axis is the relative number of electrons, just as it's labeled. Part A asks, based on the spectrum, write the ground state electron configuration of the element. There's more, but let's just do this part right now for A part 1. We need a ground state electron configuration. So we're going to start with the peak that's farthest to the left. And the reason this peak is of interest to us is that it's got the largest binding energy per electron here. And sometimes with these PES spectra, we see the x-axis goes from largest to smallest and not smallest to largest. So always look at the scale, right? But because it's got the highest binding energy, that tells us that this peak must correspond to the innermost sublevel. And of course, that would be the 1s sublevel. And since it's complete and it's in its ground state, that sublevel is completely filled. So that peak corresponds to the 1s2 sublevel. It's completely filled. The next peak over has the same amplitude, so it must also be an S sublevel. That would be our 2s sublevel. And then the peak next to that, all right, you'll notice is 3 times taller in terms of its amplitude. That must be a P sublevel, and it's also completely occupied. So that is 2p6. Next, we've got our 3s2, followed by 3p6, and then finally 4s2. All right, so the taller the peak, the more electrons occupy that sublevel. The higher the binding energy, the closer it is to the nucleus. So, all that said and done, here's your answer. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And that's really what you had to write. You didn't have to say how you got there. You just needed to get there. And that's 1 point if you had the right electron configuration. Part 2 of Part A says identify the element. Well, we just wrote the electron configuration. We can count up all the electrons, or we can go back and look at our answer. It would be calcium. Now, we do expect that your answer to A Part 2 corresponds to your answer to A Part 1. So if you had made a mistake in A Part 1, the element you write down here should match whatever that is. You won't be penalized for the same mistake twice, but that's 1 point. Okay, so let's go on. Calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. Well, valence shell, what that means is that it's the outermost energy level that's occupied, right? And for calcium, that would be our 4s sublevel, which is the peak that I highlighted here, all right? And we know how much energy it takes to remove electrons from that energy level. We're given that information, right? And so now if we know an energy, we can calculate a wavelength. We know that E equals h nu, and we know that C equals lambda nu. Now, I like to do these problems by merging these two equations, right? And substituting in nu into E equals h nu, and I get E equals hc over lambda. I can rearrange that to solve for the wavelength. Lambda equals hc over E, all right? And we have to use the energy of the 4s sublevel, right? Which is one of the common mistakes with this question, I think. All right, so we can substitute that in. We know Planck's constant. We can look that up on the formula sheet. We know the speed of light in meters per second, again, from the formula sheet. We're using the energy for the 4s sublevel that we are pulling out of the PEF spectrum, and we get a wavelength of 2.03 times 10 to the minus 7th meters. All right, this was worth 2 points. It was 1 point for using the right value for the energy, using the one that corresponds to the 4s sublevel, and 1 point for correctly calculating the wavelength. How did you do? When this question was given in 2019, the average score was 2.64 out of 4. So most students earned 2 or 3 points. So if you're in that range, you're doing just fine. If you got all 4 points, kudos to you, you're doing well. If you haven't done this already, you should subscribe to my channel for more AP Chemistry tips.